Howdy! Chapter 8, Joule's Law, EMF, and Simple Circuits. Before getting to the main part of the chapter, there are two short sections. In the first, the change in electrical energy per unit time of some charge as it moves through a device with a potential difference V is shown to be just VI, where I is the current. This is the power, and the unit, joule per second, is defined to be a watt. For a light bulb with resistance R, the power, and therefore the brightness of the bulb, is I squared R. This is just a simple demonstration to show that everything you read in the book might necessarily be so. In the first case, we're going to have three bulbs, three equal resistances, connected in series. If we connect them in series, then the voltage, according to the power supply, 110 volts, will be going across all three. So the integral from one end to the other, sum of the three integrals, V will equal I times 3R. Therefore, the power, which is I squared R, for this series arrangement, the current is V over 3R, I squared R will be V squared over 9R. The reason it's 9R is we multiply the current going through each of them by the resistance of a single bulb. So the power will be V squared over 9R. If, on the other hand, we connect the three bulbs in parallel, then the integral of E dot dr from one end to the other is the same across each resistor, and so the voltage is just IR, or I is V over R. In that case, the power, when they're in parallel, I squared R will be V squared over R. 9 times as bright as each bulb when they are in series. And just to demonstrate that, here is the series connection. You can see the three bulbs glowing. If we now connect the parallel connections, significantly brighter. The second section is devoted to calculating the velocity at which charged particles are moving through a resistor when a current is flowing. This result will be needed in a later chapter and also serves to give some intuition about what is actually going on in a current-carrying wire. The charged particles are in fact moving so slowly their velocity is called the drift velocity because they are just drifting along. The major part of this chapter is devoted to becoming a master of solving all kinds of circuit problems. At last, after 7 chapters, you will be able to solve some real and practical problems. The circuit elements that will be considered are the capacitor and resistor, as well as the battery. In this chapter, we will only consider steady-state problems, where any currents are constant and the charges on any capacitor are also not changing. The best strategy for solving such problems is to start with the equation expressing the fact that the electric field is conservative. The integral around the closed path of E dot dr is equal to 0. You will see how to pick the paths to integrate around and remind yourself how to calculate the integral of E dot dr for a resistor, a capacitor, and of course a battery. If you begin with the fundamental laws such as Gauss's law and E equals rho J, you should be able to evaluate the terms that enter the integral of E dot dr for any closed loop. This has the name Kirchhoff's loop law, but to us it is the statement that E is conservative. Quite often you will need more equations in order to solve for the unknown current and charges. Usually, the fact that in the steady state, for any region, the current in is equal to the current out, supplies the extra needed equation. This is called the continuity equation and also has the name Kirchhoff's node law. Shakespeare said, "A rose by any other name would smell as sweet." It doesn't matter that much what you call these laws, as long as you understand them and know how to apply them. This equation, current in equals current out, will be used to relate currents at a junction of a number of wires, and very importantly, will tell us that the current in any wire ending on a capacitor plate must be zero. Summary. The expression for the power dissipated in the device was derived, as well as the value of the drift velocity of charged particles in a current-carrying wire. The steps required to solve for the currents in any wire and the charges on any capacitor plates in any steady-state circuit are the main focus of the chapter. If you begin with the fundamental equations, you can tackle any circuit problem. Gig 'em!